This video is part 2 of graphing polynomials. We're going to talk about the leading coefficient test so that we can decide whether the graph is sort of right side up or upside down. To look at the leading coefficient, if it's positive, then your graph is going to be similar to either the cubic function or the quadratic function, depending on whether the degree is odd or even. So end behavior is determined by looking at the degree and the leading coefficient. In the last video, we talked about the odd degree polynomials following the end behavior patterns of cubic functions and the even degree polynomials following the end behavior of quadratic functions. So the second thing to look for is the sign of the leading coefficient. If the sign is positive and it's an odd degree, it will look like this. If the sign is negative and it's an odd degree, it will look like this. And then, of course, in blue we have the quadratic functions. So even degreed functions will look like these. End behavior only, of course. Anything could be going on in between those ends. If it's a positive leading coefficient, it opens up. If it's a negative leading coefficient, it opens down. I have some examples over here on the left. We see first a cubic function, and the leading coefficient is -4. Because it's negative, and because it's cubic, which is an odd degree function, we're going to have an end behavior that follows the rules of a negative cubic function, and that's that picture. The second red equation is a quadratic, as indicated by the squared piece of the equation with the x. Again, we have a leading coefficient that is negative, and so in this case, we'll have a graph that opens down. This chart helps some students. The degree, being even or odd, goes across the columns, and the sign of the leading coefficient, being positive or negative, goes down the rows. So you just have to look for, let's say, an odd degree with a negative leading coefficient, and the picture shows you the end behavior. What you'll also see is the notation for what happens as x approaches positive infinity or negative infinity. And these are difficult for some students. It's really the notation that makes it the most difficult. And so we've talked more about that in class than anything. And you should refer to your notes from class for lessons on that notation. Let's look at this example. Those of you that were in class recall that there was a problem with it. We'll discuss the problem when we get to it, but let's start by picking apart the equation that they give us, which is y equals -3x to the 4th. So if I'm going by degree and leading coefficient to look for end behavior, the degree is 4, which is an even degree, which means the end behavior will mimic a quadratic function, meaning that it'll be an opening up U or an opening down. Again, we're only talking about the ends. The fact that it's a negative leading coefficient tells me that the graph is upside down, which is this one. So the ends should both be pointing down. Well, they've left the arrows off the choices, but the only one with both arrows pointing down is letter B. And so really this could be the only choice, but there's a problem with this graph. Can you tell what it is? I'm looking at this graph and I see 1, 2, 3 solutions that are quite obvious. In this equation that they're asking us about, the only solution is x equals 0. And it has a multiplicity of 4 because this is the only factor here with an x in it. And so this can't be the equation for this graph. Let's use this as a learning opportunity and write the equation for graph B. So our solutions, we'll use estimates based on what we see. Our solutions are x equals -1, 2, and 3. So do you know, based on those, what the factors for this polynomial would be? X plus 1 would result in a solution of -1. X minus 2 would result in a solution of +2. And x minus 3 would result in a solution of +3. Now, before we decide we're done, there's a couple of things we need to look at. One of them is that, if you recall, we had a leading coefficient that was negative. We still have these downward arrows. We need a leading coefficient that is negative. We also have to look for any special behaviors at those roots or x-intercepts. And I see a bounce right here at -1. A bounce indicates that we should have an even multiplicity. So since -1 was this factor, we're going to make that factor squared, and that will tell us that there's a bounce there. The other ones go straight through the 2 and straight through the 3. There's no little squiggle or anything there to indicate a higher multiplicity. And so it looks like we're good. This is the actual equation, sorry about that, for graph B. We're going to do the same thing with this example, and the rest of this video is simply examples to help you practice. So listen to the things that I look at, the order that I look at them in, and see if you can do them ahead of me, or pause the video and try it on your own and then look at the answer. So these are the steps to write the equation if you're given a graph. You're going to look for the zeros and the multiplicities. My zeros are the x-intercepts. Remember, zeros, roots, solutions, and x-intercepts all indicate the same thing. I have a -5. I have a -3, 0, +3, and 6. I do want to check if any of those have multiplicities other than 1. I'm going straight through here, straight through here, straight through, and straight through. Whoops, did I miss this one? All right. When I say straight through, the line can curve and probably will. What I'm looking at when I'm looking at the behavior at those x-intercepts is whether there's a bounce or a squiggle where it sort of flattens out. That would indicate a higher multiplicity. So it looks like all our multiplicities are 1, which we don't have to write when it's a 1. So the leading coefficient, is it positive or negative? Well, I need to look at my end behavior. I have one arm up and one arm down. This indicates that my end behaviors go like that, from left up towards the right. That's a positive odd degree because this looks like a cubic function. I didn't draw it very well. Looks like a cubic function, which is odd. And it's a positive cubic function. It's the regular way. It's not flipped upside down. So our leading coefficient will be positive, and the degree, not only is it odd, but I have 5 solutions, so my degree is 5. All right, now I can write my equation. I know that my leading coefficient is positive, so I don't need a negative there. And now I'm just going to use my zeros to write my factors. So I have an x plus 5 because that would result in a negative 5 as a 0, an x plus 3. What about this 0? Well, that's an x plus 0, which is just x. But that would look funny if I stick it out here in the middle of a bunch of parentheses. So I'm going to write that one in front, right after the equal sign. I have an x minus 3, and I have an x minus 6. And we discussed in class how we weren't going to worry about the actual value of the leading coefficient, that it was enough for us to use estimates here. I want you to pause the video and try this one on your own. When you come back, you should check your work. Okay, how did you do? Remember, they're giving us standard form and factored form here. So we're not looking at two different equations. We're just looking at two different forms of the same equation. They've done a lot of the work for us in the factoring. The zeros were 0, 2 with a multiplicity of 2, and negative 3. I could find those easily from factored form, which is this bottom equation. I noted that there was going to be a bounce there because when I'm writing my multiplicities, it's a good time to indicate that there's a bounce or a squiggle so that when you look back at it and you're drawing your graph, you don't forget to do those. The y-intercept in this case is 0, and we can see it here, but also you should know that in standard form, the y-intercept is always the constant. I put SF for standard form. In this case, there is no constant. A constant is a term without an x in it. And so the y-intercept being 0 can help you to draw a more accurate graph. Finally, the leading coefficient test and end behavior was determined from standard form. And while you can find that from factored form, it's very easy to look directly at standard form and say I have an even degree, so it's modeled like a quadratic, and a negative leading coefficient, so that it's an upside down quadratic. And I always make a little sketch so I know in the end that my result should also have both arrows pointing down. Finally, it's sometimes helpful to pick a few in-between points. I won't require this in class, but you should know that if you need a more specific graph at any time, you could say plug in to one of your equations a -1 and find out exactly where this point is. And you can do that with any point. In summary, the vocabulary for this is extensive, but these are terms you already know mostly. The new one is probably multiplicity, so make sure that you know what all of these words mean. We use all of them to describe the graph or equation of a polynomial. Remember, everything relates back to either the simplest even polynomial, which is y equals x squared, or a quadratic equation, or the simplest odd polynomial other than a linear equation, which is y equals x to the third, which is a cubic equation.